There we go. Pretty sure I hit the right buttons. So do that and all right. All right, so we now know the angle at that speed. I'm going to change it to a smaller angle, lower speed. So let's make it 30 meters per second. Instead of 50. And because we didn't plug numbers in too early, it's simple enough of just changing it there. So arctan at 0.9. All right. Presumably, some of you can guess what we're doing next. Friction. Throw friction into it. So now I want to figure out the maximum and minimum angle so that it will not slide. Assuming it's still going 30 meters per second. We'll have mu s of 0.8. So first, let's figure out the minimum speed. So if it's at the minimum speed, which way is friction going to act on it? Friction up this way, and so we end up with friction like that. So this would be F cosine theta, F sine theta. Yeah, I may as well clean this. All right, what are my two equations? In unison, be really cool.
Is it y sine theta is equal to NA minus F cosine theta? Oh.
And the other one? James, you gonna go for it?
F sine theta minus y cosine theta? Or is it plus cosine?
They're in the same direction. So plus. Nope. Soon.
Minus weight.
Equals 0.
All right. Two equations, two unknowns, just like before. So we now have, all right, I'm tired of writing sine theta and cosine theta, so I'm gonna go to my usual substitution here. I'm gonna let S equal sine theta and C equal cosine theta. So I have ys minus mu yc is equal to mv squared over r, and fs and mu ys plus yc is equal to mg. I don't know theta. I don't know y. So I don't know normal force, I don't know theta. Those are my two unknowns. I need to get rid of something. Getting rid of normal force makes the most sense, since I don't need to know what the normal force is. So factoring it out, I have y sine minus mu cosine is equal to mv squared over r, and y mu sine plus cosine is equal to mg. I'm going to divide again, just to get rid of my y's. So I'm left with sine minus mu cosine over u sine plus cosine is equal to v squared over gr. Now notice if the friction goes to 0, the mu terms drop out, I'm left with sine over cosine, tangent of theta, which is what we had before. So I should feel like something is going right, the fact that I can easily turn it into the previous problem just by making it frictionless. So now my only unknown is theta, but it's wrapped up inside these trig functions, so how do you deal with it? How do you solve this? This is equal to some number that we could calculate if we need to. I'm just gonna call this A, just so I don't have to keep writing g squared over gr. Sine theta minus us cosine theta over us sine theta minus cosine theta, plus cosine theta is equal to how do you solve for theta?
I guess there's a trig identity for this.
Not here, or not to my knowledge. I guess we probably could create one. All right, so first off, I've got theta in the numerator and denominator. It generally, unless I can cancel something out, having it in the numerator and the denominator, not a particularly easy thing to deal with. So how do we get rid of the fraction?
Both sides.
All right, so we end up with sine theta minus mu s cosine theta is equal to a times us sine theta plus cosine theta. I'm going to distribute, so sine theta minus mu s cosine theta is equal to a mu s sine theta plus a cosine theta. Now what?
You could mess with it to get the cosines.
So what were you thinking?
I was thinking it might help to get the cosines on one side, the sines on one side.
All right. So I got sine theta minus a mu s sine theta is equal to us cosine theta plus a cosine theta.
Factor out the sine from the left side and cosine from the right.
So I got sine theta,
Sine
1 minus a mu s sine theta, times a mu s equals cosine of theta, us plus a.
Divide to make a tangent.
So if we bring cosine over to here and this over to there, we end up with sine theta over cosine theta, or tangent of theta, is equal to mu s plus a over 1 minus a mu s. So let's do it. So that's 0.8 plus, I don't suppose anyone's figured this out. Oh wait, that was 1,000, that was 30, that was 0.9. Over 1 minus 0.8 times -0.9, which is 1.7 divided by 1 minus 0.72, 7 over 0.3. 0.28.
$80.65 degrees.
We were trying to find the maximum angle at which it would not slide down. So as it creeps up, that's like, at some point it's gonna start sliding down, so we found that maximum angle, 80.65 degrees. I think I might have said it backwards before.
It
Pardon?
doesn't seem right. But, you know.
You're traveling at over about 65 miles per hour.
Oh, okay.
Friction's your friend. Now, I'm sure there's some realities that would change that number.
That would assume like the center of mass is like
Right.
right at the concrete or the pavement, not somewhere above.
Would it?
I mean, because it could roll.
Yeah, we are assuming that it's not going to roll. Because as you're going faster and faster on that, no, we're definitely assuming it's not gonna roll. That's later. You can go through a similar process to find the minimum angle to which it will slide at that speed. Friction flips around, negative sign shows up a different place, and you end up with what I suspect will end up being a negative number. But suppose you do get a negative number. What would that mean?
The negative number for what? The angle?
The angle.
Didn't you say that was the minimum? That's the minimum angle until.
Okay, you're going around the track like this.
Mhm.
Well, what a negative angle would be like that, so you're now on right here going around.
Yeah, basically saying that as long as the angle is in between 0 and 90, you're not going to start sliding down.
Up.
Slide up.
Not gonna slide up. Yeah. Actually, when we did this before, the first problem we did, it was on flat. What was the speed for the first part?
I think we were trying to figure out the speed the first time.
What speed did we get?
28 meters per second.
So this is more than that. So in this case, the angle probably will not be negative. It'll be some small angle. All right. Anyway, centripetal motion problems. You've got swinging things on a string. Also, you go through the exact same process. They're all the same. Questions before I expand our universe?
I'm sorry. Thank you for posing.
like Carol Merrill. Sorry, she smiles. All right, so let's talk about force due to gravity. What's the requirement for force due to gravity?
It has to be a relatively small, an incredibly relatively small mass compared to the body that is causing its gravitational pull.
That's what we call weight. That's just a specific case. I'm talking more generalized. What was the requirement for there to be a gravitational force?
Just two bodies with mass.
Two masses. It's classical physics. All right. So whatever the formula is, if I'm dealing with a force due to gravity, it's got to have two masses in it. It should be commutative, because if there's a force between me and the box right there, it should, if I look at it from the other point of view, Newton's third law says it should be the same magnitude of force no matter which mass point of view I'm looking at. So the masses should commute. Well, I've got two operations that commute, addition and multiplication. Division definitely doesn't commute, subtraction doesn't. What I mean commute is you can flip the order and you get the same answer. Now, the larger the mass is, your gut feeling, the larger the pull, the less the pull.
Larger.
All right, so whatever this formula is, and I'll just spoil part of it, they are multiplied together. It is in the numerator. What about distance? As in, do you think there's a greater pull the closer you are or the farther you are away, or no, distance makes no difference?
It would be greater the closer you are.
So as r goes up, the force would go down. As the distance goes down, the force goes up. I think that's what you just said.
Yes.
In fewer words. So r is on the bottom, and not really well, I'll do a slight justification in just a second. It's squared. And this is the essence of the formula right here. It's the product of the masses over the distance squared. Now the distance squared, if you think about it this way, is that somehow there's some signal being sent back and forth between the masses. And if you think about the signals being sent out in every direction. So if I, like a homing beacon, it's sending it out in every direction. As it moves out, as the sphere gets bigger, well, I have whatever signals being sent out gets spread out over the surface. So the bigger it is, the smaller the signal gets. And it's being spread out over, well, the surface area. What's the formula for the surface area of a sphere?
Uh, 4/3 pi r cubed.
That's the volume.
Oh.
Take the derivative with respect to r.
So 4 pi.
R squared.
That's the surface area. And so whatever the signal is will get diminished. It'll be distributed over a larger area, diluted. That's the word I'm looking for. It'll be diluted with respect to the area, which is r squared, and that's some justification. There have been some groups, I don't know if anyone is still doing it, but there's this group called the Particle Data Group, which basically keeps track of all the minutia with physics. And there are been some people who've been trying to figure out, is it really squared? Maybe it's 2.00000001. And so they basically are trying to figure out the difference between what the actual number is and 2. And at this point, they've narrowed it down to the difference is less than, like something like that. So they don't know what it actually is, they just have a bound. Classical physics, it's squared. For anything that you do in physics, it's squared, unless of course you are trying to figure out if it really is squared or not, then you care, but other than that, squared is good enough. Now, I did leave a space up front, and this depends upon what unit system you're working in. So, if we're dealing with the SI system, that's in newtons. Mass would be in,
Kilograms.
so that would be squared. Distance would be,
Meters.
so I have this factor here that has to somehow resolve the units. And so if it's in newtons meters squared per kilogram squared, the meters squared and the kilograms squared would cancel out. I'm left with newtons. It's mathematically sound, at least as far as the unit goes. And more specifically, this is represented by a capital G. This is the gravitational constant. Let's at least change colors here. Gravitational constant. I don't think it seems like it's been a while since I've seen it. At some point it was called the universal gravitational constant, but then it came out of, how do we know it's universal? I mean, it's constant, sure seems constant everywhere around here, but in another galaxy, is it still the same? So I might sometimes refer to it as universal gravitational constant, but gravitational constant is better. And in it, the SI unit version, G is equal to 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. So, my mass is about 100 kilograms.
Okay, so let's just make so it cancels with the units.
Yeah.
And we get newtons.
Yeah. There are, when you start getting into the theoretical realm, they deal with what are called naturalized units. And in naturalized units, you have constants like the speed of light and gravitational constant, which are equal to 1.